So we're going to look at an example using binary regression. Pretty simple introductory stuff here, and we're going to look at the output that Excel gives us, how to interpret those things, and then looking at goodness of fit measures. So here's the data set that I have us to look at. It is Hillary 1996, and I took from the National Election Survey, NES data, and I selected just a few of the variables here randomly, so that's why it says random 200. I took 200 variables. One of the things to notice here too, and this is the very first thing we're beginning with Excel, and that is when you're running regression in Excel, is that before we run regression in Excel, one of the things that Excel cannot handle is if there is missing data. So you'll notice as I scroll down the rows here, it ranges from, as it says at the top, from 2 to 201. So here's a 201th observation. Each of these rows represents an individual, a respondent, right? Survey respondent. You'll notice that there are no blank cells. If ever you have an instance with a blank cell, Excel will not be able to handle it. If you do it with a stat package like R or Stata, what it does is a process called list-wise deletion. All that simply means is if I had, for example, this cell, let's say this number 13 here, was missing, just blank, right? What the stats programs will do is it would delete this entire row, hence list-wise deletion. If you have even one missing variable that is included in the regression, so assuming that income was either the dependent or one of the independent variables, you would have to completely delete that entire row. There's no other way to do it, right? There's no other way to handle that missing data. So the problem, though, is that Excel is not really built for that kind of data analysis, right? The regression thing is sort of built in as an additional add pack, so it doesn't know how to handle that. So if ever you're encountering an instance where there is missing data, you would simply have to delete all of those rows. So for example, if that income variable is missing, the easy way to do this, of course, is you could just sort all of your variables one by one, and then using the sort function under data, and then make sure that none of them are blank. For the purposes of this class, though, I don't think I'm pretty careful to never give you missing data, but I want you to be aware of that, of list-wise deletion if you ever have missing observations, that the entire row, that entire person essentially, we would have to drop them because of that missing variable. Right. Now, if it's something that we're not using, it doesn't matter. So if I run a regression, for example, on the Hillary Clinton feeling thermometer variable and religion, not that I would want to do that, but if I did that, I could, it would still run because I'm not using one of the missing variables, right? So it has to have it has to have all the components of those variables you include in the regression. So let's start by looking at this data. We have, as I mentioned, a subset of NES data. We have male, coded as 1 or 0, a Hillary Clinton feeling thermometer from 1996. I don't know why they're asking. This is when she was the first lady. I don't know why they're asking back then, but okay. This ranges from 0 to 100, so it's 101 possible values. Technically not continuous, but it basically, because continuous, remember, you could break down to even smaller and smaller parts. But here, of course, the smallest you can break down is to one incremental unit, right? So you could have like 51 or something like that, but you couldn't break it down. In fact, all these are 5s. I guess you probably couldn't. It's probably, in that reality, it's probably even less continuous than a normal feeling thermometer. It probably looks like you can only move in increments of 5. But either way, as we mentioned before, when you have continuous variables, when you have ordinal variables that assume many bins, right, many categories, it essentially looks like continuous data. And for the purposes of estimation, we can generally treat it the same way. So we're basically going to treat this like it is continuous. In reality, it's actually an interval, right, because it only ranges from 0 to 100, and it can't go negative, it can't go past 100, which continuous would require, right? We have income, which is a 1 to 24 point scale. I don't know what the 1 represents. It's probably like under $10,000 a year, and 24 is probably like maybe over $1 million. I don't really know. But it's an ordinal variable that goes from 1 to 24, and I assume that it has probably some sort of standardized increment, right? Not really clear, but doesn't really matter for our purposes. And then for religion, we have a categorical variable, also called a nominal variable, in this case a multinomial variable, because it has multiple bins. The numbers assigned to these are completely arbitrary. I have no idea what they are. I'm assuming that, well, let's look at the modal category. Equals mode D2 through D101. I'm sorry, 201. The modal category is 1. I'm assuming, given the demographics of this nation, that 1 is probably maybe Christian, or maybe Protestant, maybe, something like that. I don't really know, right? And that's the point about these categorical variables, and why, remember, when you're thinking about running categorical variables in regression, it would be meaningless to do it as is. So sometimes I'll ask this as a test question. Why would I not want to use this as an independent variable to predict something like the Hillary income variable? Now, in reality, it might make, I'm sorry, not income, the Hillary thermometer variable. In reality, you might think, well, wait a minute, maybe Christians are less supportive or more supportive of Hillary Clinton. You might be right, but look at how these are coded. They're arbitrary, right? I don't actually know what they are, and I could completely change the numbers up. I can make Christian now be a 9. I can make Buddhist a 3. I can make Jewish a 2. The numbers I've assigned to these are completely arbitrary. They're simply numeric placeholders. Right? Now, if I wanted to make it into something meaningful, so let's start with perhaps this first exercise. Since if I ran a regression of religion as our independent variable with Hillary feeling thermometer as our dependent variable, it would be meaningless. But I could make it meaningful if I extracted just some of them. So instead, what if I did something like this? Let's assume for a moment that 1 in the religion column represents, let's just say, Christian. What I could do then is I could change this and then into something that might be more meaningful. So for example, I could do something like this. How about I call this one Christian. I'm going to make a new variable next to, I don't need that apostrophe, next in the G column. And I'm going to create an if function to filter out Christians from non-Christians. So instead, I'm going to do something like this. Equals if, open parentheses. Now I enter my logical test, meaning what do I need to prove to be true, followed by a comma. And then tell Xdata what to do if it is true, and then what to do if false. So what if I want to create a variable where if D equals 1, assuming that represents Christian or Protestant or something like that. In this case, I'm assuming it's Christian. If it is a 1, return a value of 1. If it's not, in other words, if false, return a value of 0. You notice too, as I moved across, it started bolding the thing. So it's telling me, look at what it's telling me to do with the syntax. Logical test first, and if you don't know what that means, you can click on it, it'll give you an example. So in this case, I'm going to say, I want if this cell equals 1, return a value of, and then comma, look what it did, move to true value, and it tells you how to do that. Return a value of 1, comma, return a value of false, 0, close parentheses, and look what it did. It spit back a 0. Why? Because the 9 does not equal 1, it equals 9. So I could copy and paste that, oops, too far. I want to go all the way down. I could copy and paste that all the way down, shift page down, all the way down to the 201st observation, which is our total set. Now look what it did. It gave me 1s for Christian, presuming that the 1 over here equals Christian, and then 0s for other. So now look what I've done. Now I have something that's meaningful, isn't it? Because now I could say, let's assume well, we could actually run a regression on this in just a second. But now what I could say is that being a Christian results in a, whatever the coefficient will be, positive or negative decrease in the Hillary Clinton feeling thermometer, right? And then I could say other would result essentially in whatever the intercept was, because 0, well, we'll get to that in a second. But basically, I now have something meaningful. I've taken something meaningless and I've made something meaningful. Now let's assume for a moment that it looks like we got a lot of 9s over here. What if we assume that instead of this being Christian, this was something like Protestant, and then 9s were something like maybe no religious affiliation? I could create another variable that does the exact same thing. Return a value. So let's assume this is no religious affiliation. So non-affil, we'll call it AFFIL. Doesn't really matter what we name it, right? And I'm going to do the same thing. Equals if, open parentheses, pick from the same thing, D2, equals, but this time I'm going to say 9, right? Because I want to know if it's 9, comma. Now if it's 9, I want it to return a value of 1 if true, so comma 1, comma 0. See what I've done? So now I'm saying logical test, if this value equals 9, return a value of 1. If not, return a value of 0. Close parentheses, and look what it did. It returned a 1. I could copy and paste this all the way down again. And now I've created 2 variables that are perfectly not correlated with each other, right? I'm sorry, I should say not correlated. They're perfectly independent of one another. In other words, you can only be one religion, right? You can only pick one option from amongst this list. You can't pick 2. So, in other words, there's never going to be an instance where somebody is both Christian and non-affiliation, right? There has to be one or the other. That sort of makes intuitive sense, like how you could never be both male and female. You can only respond as one, right? 1 or 0. So what I could do then is these are, by the way, called dummy variables or binary variables. They're called dummies because they can only assume 1 zeros, right? And that's where the idea of binary comes in. So what I could do then is I could create a series of dummy variables for all the possible religious affiliation categories. We know that there's 9 in total, right? So if I knew what they were, I could then create up to these 9 dummies, which captures all these possible religious responses, right? And so going down the road then, so we have like, Christian, Muslim, Buddhist, non-affiliation, atheist, all the way across for all the possible 9 categories, ones or zeros, right? Now we'll be able to plug those things into the regression model and actually get something meaningful out of it, right? Because then I'd be able to say, okay, being non-affiliated with religion has this effect on the Hillary thermometer. Being Christian has this effect, because assuming these 1 or 0 values. But again, if I did it like this, I couldn't really make that assumption. I couldn't make that interpretation because the values here are completely arbitrary. Here, they have now taken on the value of indicators, right? They're indicating whether the presence or absence of something. Okay, let's start with a really basic regression. We'll come back to this with a little bit more detail. So remember, to do regression, you need to go to File, you need to go to Options, if you haven't done this already. Go to Add-ins. Add-ins. There it goes. Click on the Analysis Toolpack, click the Go button, make sure the Analysis Toolpack and Toolpack VPA. I think all you really need is the Toolpack. I don't even know what the VBA does, but whatever. We'll just click both for the hell of it. Go over to Data, and then there's your data analysis. If it doesn't load right away, you might have to restart Excel. Sometimes the newer, like 2016 for some reason is a little wonky. You got to restart the whole thing and kick it back open. Okay, so we want to run a basic regression. So we'll go to Data Analysis. We have regression as an option all the way at the bottom. Press OK. Now remember what it asks us. So you can tell I've been tinkering with this because it already has some values in here. So let's go ahead and delete all this out. We'll start with a blank slate. So this is how it looks blank. It asks you for your y, which is your dependent variable, your x, which will be your independent variables. You can actually have more than one when we'll be doing, there's a whole chapter devoted to this on multiple regression. And it'll be just as easy to do it for multiple regression too. You'll simply, instead of selecting one variable, you'll select multiple columns of variables, right? Now, one thing to note about this and to keep this in the mind for the future, for bivariate regression, when you only have one independent variable, one x, and one dependent variable, which you only will ever have one dependent variable, you can, they don't have to be next to each other, but I believe when you have multiple regression, meaning you have multiple x's explaining your dependent variable, your y, they have to be next to each other. Otherwise, it will kick back an error about them not being contiguous. Contiguous meaning they're not touching, right? So let's start with a regression. With our dependent variable is going to be the Hillary Clinton feeling thermometer, because it's basically the closest we have out of here that is a continuous variable. And remember, regression can only be used in continuous measures, right? Now, technically, we can sort of force Excel to spit out results even when the measure isn't continuous, but it should only, technically, the restriction is that it should only be used for continuous variables, right? So first thing I want to do is I have labels, and I want to keep these labels because when it spits out the regression, instead of it just saying variable, it'll tell me the label of the variable. So it's easier to remember, easier to interpret, right? So I'm going to select my range. I could either click this and then drag it all the way down, or you can type it in, which is considerably faster. So I know that my range is going to go from B1 all the way down to B201. Now, remember, I'm including B1 because I've clicked labels, so I'm going to include that first cell, and then that's telling Excel that keep that first cell, that top, as a label. So I'm going to type B1 colon B201. And now my independent variable, let's do income for this one, right? So that is C1 through C201. Okay, now we can ask it where it's going to spit it out, new workbook, whatever. Let's just have it spit as the new worksheet. So it's going to spit it at the bottom of the, it's sort of off the screen right now, but it'll show up as a new tab, right? Press OK. And it spit it out. So let's zoom in a little bit, see what we got. Let me move this guy down just a wee bit. Maybe we can see it. There we go. So it spit out from the data sheet to sheet 3. Yours will probably say sheet 1. I've been sort of tinkering. That's why mine's doing sheet 3. Take a look at the data that it's given us. We don't need that. Okay, cool. So let's move this out. There we go. We've got our multiple R statistic, R squared, adjusted R squared, standard error, number of observations. We've got our sum of squares, residual regression sum of squares, residual sum of squares, total sum of squares, mean sum of squares, F statistic, and then most importantly for our purposes, we have our coefficients, also known as our beta, right? Our beta coefficient. Here's our intercept, also known as our constant. Here is the coefficient for income, and then here is the standard errors, the T statistic, and very importantly, the p-value. So we can see by looking at both of these, they are both statistically significant at the 0.05 level. In fact, this one is significant at the 0.001 level, right? You can see that it's less than 0.001. In other words, it's statistically significant at the 99.9% level. This one is in scientific notation. It says there are negative 32s and then a 3 and then a 1. So in other words, what we need to do is we would have to put 30. It'd be 31, and then we'd get to, then the decimal point would be, and then this the 3-1 would appear. 31 zeros, so it'd be point 0.000000000, a bunch of zeros, 31 zeros, and then 3-1. So this thing is significant at like the 99.9999999. It's definitely significant, right? No doubt there. So that's cool. We got it. We got something there. So let's begin with the very first and most important step that I always try to drill into your brains: interpretation of the coefficients. So remember what our dependent variable is. It's not listed here, which is kind of annoying, but we know we only have one dependent variable to remember. It was the feeling thermometer for Hillary Clinton, ranging from 0 to 100. Right? Let's assume it goes in increments of 1. In reality, it goes in increments of 5, but let's just assume it goes in increments of 1. So how would you interpret that? The way you'd interpret it for this coefficient is for every 1 unit, I'm talking about this income variable, for every 1 unit increase in the that did not show up at all. There we go. In the income variable results in a decrease of 1.0105 in the Hillary Clinton feeling thermometer, right? All other things held constant. Remember, this is a linear function, so every additional unit in this will result in this change in the support for Hillary Clinton. So in other words, as we see income going up, support for Hillary Clinton is going down. Not that surprising, right? Perhaps, because typically we see lower income individuals tend to be more likely to vote Democrat, and on. So maybe this sort of makes intuitive sense. And we both know that they're statistically significant too, right? Now, what if it were possible for a respondent to have an income score of 0? We know it's not possible because the income variable ranged from 1 to, I want to say like maybe 20, 25, 24. Here it's 24. Maybe it went up to 25 and we just didn't get all the data, but it looks like it caps out at, well, we could look at that easily by figuring out. We could figure out the maximum by just typing max. And then doing, what is income? C2 through C201? It's 24, yeah. So let's just assume that's the maximum value. So it's not possible for somebody to have reported income of 0. But if they did, think about what that would mean, right? It would mean that all you're left with is this intercept, or it's also known as the constant. It's also known as alpha, right? So what do we mean by that? Remember what we're doing. We're trying to create a prediction for y. This is called y hat, right? Y hat is the expected value of y given what we've observed, right? Now, we know, though, that our expected value, in other words, this is our actual value for y, because this is the observed value that the respondent has given back. Our y hat is what we would expect them to say, right? So we know then that these estimates are not always going to be exactly accurate because they are exactly that. They are estimates. They're predictions based upon this variable, right? So we know that there's going to be error around that. Now, you might recall that there's a term for this distance, and this is called the residual, or the error term. Let's go to the slide and see what we're talking about. So this is taken directly from the book, right? Remember, this is the sample regression model. We have our values of y, which we directly observe, are now our constant, or intercept, as it's called, right? Our alpha hat, which we've predicted. That's why it has a hat on it. Our beta hat, which is this guy, right? So here's our alpha hat, our intercept. Here's our beta hat. We've estimated these things, right? And then we have some error term. So take a look down here. So once we now have generated these predicted values of y, right, in other words, what we think y would be if our model is correctly specified, sometimes it's not going to fit, right? And in fact, that's what some of these estimates of error fit are telling us. So let's recall what some of these mean, and then we'll go back to the math of what these things mean. So the first one, the most obvious one, is the root mean squared error. Now let's go down to show you the formula for that one. Further down. Where are you? Uncertainty. There it is. Root mean squared error. This is taken directly from your book. Let me see if I got the page number here. Section 8.4.1, I think is what it is. So this is the root mean squared error. Take a look at what it's telling us. It's taking the sum of all of those errors then. In other words, the sum of all the distance between the observed y's and the estimated y's, or the distance between y and y hat. Right, so y minus y hat. You're squaring all those up, summing them all together, and then dividing by the total number of observations, and then taking the square root of that. Now, luckily for us, that is reported right here. They call it the standard error as opposed to the root mean squared error, but it's the same thing. So this is one of the first measures of model fit, and this one is perhaps very intuitive. What this is telling us is that what we're seeing is that the average gap between the expected value of y, meaning y hat, and the observed values of y is 27.5 points off. In other words, we have a big sort of error around this. And the reason why is pretty obvious. We're only using one variable, income, to try and predict your support for the Clinton feeling thermometer. There's probably a lot of better things that might predict that, right? We saw that it was a statistically significant variable, right? But it doesn't have a whole lot of explanatory power. Now, how did they get that? How are they calculating this? Well, look at the formula, right? We would need to know the residuals in order to calculate that. Let's go back to this and run another regression so we can actually see what those residuals are, what they look like. Let's run our regression again. So go over to data, go over to data analysis, go back to regression. It should still automatically be saved. It sort of remembers what you did. Now look what it's already done here too. It's also remembered what I selected, so I don't have to actually reselect anything. I can keep it everything I had it before, right? Keep the label sync checked. Great. Now look what I'm going to do. I'm going to click residuals, right? And then press OK. It's going to spit out another sheet. Here it'll probably be called sheet number 2. Now, take a look what it did. It spit out the exact same values that we had. Right? All of this is exactly the same. The only thing it's done is it's now given us the residuals, right? So it's actually done a few things for us. So what it's done is it's done the predicted value of y for every single person, for every single observation that we had. We had 200 people, right? 200 respondents. And then what it gave us is, assuming this is true, this is the predicted feeling thermometer for Hillary Clinton for that person in observation 1. Now, how did they get that? What they did is they go back to the data, look at number 1, look at what they put down for income, right? So what they did is, I'm sorry, that's not number 1. There's number 1. So number 1 reported a value of 16 for their income, 16 out of 24, and they gave Hillary Clinton 100% on the feeling thermometer. So what they did to calculate that is, so this is the exact same, this is going to equal the exact same as this. They took 16, because that's what they reported for income, right? They multiplied that times the income coefficient, and then they added in the intercept. And then we got the exact same number. Right? The only reason it looks different is this has more decimal places, but it's the exact same number, right? That's how they're getting it. They're simply plugging in whatever the person put for income, multiplying it by the coefficient, and then adding in the intercept. And that's how they're getting the predicted value. So this is the y hat for every single observation, right? Excel will give that to us. They also will give us the residuals. How did they calculate that, right? So the way that they calculated the residuals, so actually let's just highlight these so we can see what we're, well, no, that might just be confusing. We'll just keep moving on. So how do they get the residuals? What they did then is they said, okay, well, let's take a look at what they actually put. So let's go back to the data again. So observation number 1, see it's numbered here, right? Observation number 1. Observation number 1 put 100% of the Hillary Clinton feeling thermometer. So what they did is they said, okay, that's y. This is y sub I. This is what individual in observation number 1, individual 1, let's call them, put down as their answer for y, the Hillary Clinton feeling thermometer. Now minus what we predicted their value to be. We predicted that they would, I'm sorry, I forgot to put an equal sign. There we go. Equals 100 minus their predicted value, their y hat. So this is essentially, all I'm writing here is y minus y hat. Now look at what I get. I get the exact same number as the residual. All I've done is, for each of those observations, back to this guy, where is it? There it is. Come on. Not that one, this one. So what we've done to calculate those residuals, right, is I simply look at the difference between the y value, the actual value we observed, the y hat value, what we've estimated. So take a look here too then. That y hat is going to be equal to the estimated value plus the residual, right? So in other words, if I added up y hat, which is this one, I'm sorry, y hat, which is, well, that is the same thing. These are both y hat. If I did y hat plus the residual, it would equal the actual number, right? So let's label these. This is y hat. We'll just leave it like that, right? Y, it's y with a little, triangle thing over it. This is the residual, or error, if you will. Now, if I added the y hat plus the error, what do you think I'm going to get? You can probably tell just by eyeballing it. I got the actual value of y. This is the observed y, right? That's what we're getting out of this. So we could actually do some of the cool stuff that you need to do to determine model fit. So let's look at some of the other ones. We just mentioned root mean squared error. As I mentioned, you could manually calculate that. It's kind of a pain in the butt because what you'd have to do is you'd have to sum up all, you'd have to square all these residuals. So I'd have to do all of these residuals, square all of them, right? Then I would have to add them all up, the summation symbol, divide by the number of observations, 200, and then take the square root of that. Now I could do that, and how it would look, in just to, if in case you're curious, if we wanted to calculate it, we would do something like this, equals this guy, we're going to square him, which is a caret and a 2. So this is, let's label these, this is residuals squared, we'll just abbreviate. Then now we need to sum them all up, so let's copy and paste this all the way down. Whoops. So we need to do this for every single cell. For the 200 observations. You do not have to do this, of course. This would be a complete waste of your time. Equals the sum of, what is that? This is G25 through G224. G224, close parentheses. I've now got the sum of them, right? We could actually combine this into several steps, but let's just do it into a different one. So now I have, this is the sum of residual squared, right? Now I need to take the square root of that and divide by the number. So this equals SQRT for the square root of this guy, divide by, there's 200 observations, close parentheses. And then I get my result. Take a look at what I got. This now is the mean squared error, or the root mean squared error, excuse me. I knew I was forgetting something in there. So this is root mean squared, Jesus. There we go, if I could type today. Now take a look. This number is exactly identical to this number, right? The standard error that Excel reports is the exact same as a root mean squared error. So again, what is this? What does the root mean squared error tell us? It tells us that our model has an error of about 27.5 points. In other words, we're not doing a super great job, right? There are other methods of determining model fit. We have also the R Squared Statistic, which can be calculated in a few different ways. So they say first we need to calculate the total sum of squares. You would do that by subtracting all those observed values of y. So you would do all of these observed, I'm sorry, not all of these values of y, all of these values of y, and you subtract that from the average of y, which we could just do by typing equal average and then do B2 through B, 201 or whatever. And then you would square all of them and then sum them all up. Right? So we could do that. Thankfully, we don't have to. The total sum of squares is also calculated for us. The total sum of squares is listed. Let's do a different color. Listed right. Oh, I did not mean to do that. Is listed right here. Let me make that a lighter color. A little easier to see. There it is. Right? See, total sum of squares. Kind of nifty. Right? You'll also notice one other number that looks pretty similar too. Notice, remember how I called this the sum of residuals squared, right? Sum of squared residuals. SS, sum of squares, residuals. Look at this. This number and this number are the exact same too. The only reason they look slightly different is because this one, you can't see the decimal places, but if I pulled it out, you'd see exact same. Now, thankfully, we don't have to do that, right? So the things that they already give us, if we want to label these, maybe we could label them a little bit better. So this is, let's put them here because we don't really need the degrees of freedom. Let's delete this and we'll rename it. So this is our RSS. This is our TSS, our total sum of squares. Right? Let's put an arrow so we know where we're doing it. Doop. Right? They're labeled for you. You just have to kind of see where it is. Okay, so that's cool. So we actually have both of these already calculated for us, right? We didn't need to do that. Excel spits it out. So what can we do with these things? Well, we can then calculate the R squared. There's actually a few ways to calculate the R squared. You can do it like this. You can take 1 minus the residual sum of squares divided by the total sum of squares, or you could take as they have here, another way to calculate it, the model sum of squares, and then you divide the model sum of squares by the total sum of squares. Now, if you're thinking, they gave us RSS, they gave us TSS. I wonder if they gave us MSS, the model sum of squares. They did. It is right there. Now notice it's not here, right, because this is the model residuals. Look at the line here. So I don't really know where to put this. I guess I can just there's no down button. Well, just remember what I'm telling you. So model sum of squares is just right there, right? Let me bold it. Actually, no, we don't need to bold it. We can do, Yeah, we'll go ahead and bold it. So now, and to prove that we're right, look at one of the ways we can calculate. Let's just do them by hand since we already have these. So let's do 1 minus RSS divided by TSS. Let's just see if we can. I don't know if I can copy this. Oh, no, I cannot. Maybe I can. No, I can't. Okay, let's just remember 1 minus RSS divided by TSS. So we'll say 1 minus RSS divided by TSS. This is one way we can get R squared, right? So let's do it by hand. Equals 1 minus, where's the RSS? RSS there, divided by this guy. Now take a look. This guy, let's use a different color. Let's do, what have we not used yet? How about red? This guy is exactly equal to that guy. Shocking. Mind blown. Now let's do it the other way. Let's do the model sum of squares down here. Model sum of squares divided by the total sum of squares will also give us the R squared. So model sum of squares divided by total sum of squares, also R squared, right? So equals model sum of squares divided by total sum of squares. Ta-da! Same thing. Mind blown, right? Now, what are we doing with the R squared? The R squared tells us a way to look at model fit. I think it's on the next slide what it says. No, maybe this one just, yeah, I guess this is the one that does it. So, or is it, let me see, hang on, I'm sorry, keep clicking around. Okay, there it is, good, this is where it is. So, look at this slide. The R squared statistic, this is taken from your book too. If you forget this, you can read it, it's directly in there. They're easy to find. These things, these images of the formulas are directly copy and pasted. The R squared ranges from 0 to 1. What does it tell us? The proportion of the variation explained in the model. So let's turn back to this. What this is telling us is that our model explains 5%, right, 0.05 is 5%. Or technically, if you want to be technical about it, it'd be 5.411%. We can just say, basically 5%. It explains 5% of the model variation. This model explains that model variation in our dependent variable, right? Hillary Clinton feeling thermometer. Basically not good. This thing ranges from 0 to 1. It will never be negative. It will never exceed 1, right? It's always going to be 0 to 1. 1 would be a perfect prediction. And in fact, if you ever did that, Excel will say error because you can't perfectly predict something. Because then you basically have basically a proxy for the dependent variable. So what was I going to say? Oh yeah, so if we had something like maybe 0.8 or 0.9, that would be a really good model fit. Here we can see not so great, right? Not a really great one. We're at the very low end. Now, one of the downsides about and so one of the things we can do with this, let me start with that. One of the things we can do with the R squared then, and with the standard error, is it allows us to compare between models. So if I ask you a question on homework or the exam, and I ask you something like this, run a regression between with male as the independent variable. We're both going to have the same dependent variable, Hillary Clinton feeling thermometer. Actually, let me just let's do it. Let's do the example, so that way I'm not confusing people. Let's go to data. Let's go to data analysis. We're going to run another regression. However, this time we're going to change something up. We're going to keep our dependent variable as a Hillary Clinton feeling thermometer, but we're going to change our independent variable to male. So it's going to be A1 through A201. We don't really need the residuals, so let's unclick that, and let's spit it out. Look at what we got. Now, we have, we can see intercept remains statistically significant. It's at 60. This coefficient is statistically significant at the 0.01 level, the 99% level, but not at the 0.001 level, meaning not at the 99.9%. How do we know that? Look at the p-value. So I can see that this is less than 0.05, which would be 95%. I can see it's less than 0.01, which would be 99%, but it is not less than 99.9, which would be 0.001, right? So if I ask you, is this 95%, is it significant at the 95% confidence level? Yes, no problem, right? And we can see that being male makes your support for Hillary Clinton go down by 11 points, 11.9, or basically 12. So remember how we interpret coefficients. A 1 unit increase in X, in this case, a 1 unit increase in male, will result in a, in this case, 11.98%, or 98 point, I should say, decline in the dependent variable. Always drill this into your brain. Keep saying it out loud. Say it in the shower. A 1 point increase in X, whatever X is, here it's male, will result in a beta coefficient, in this case it's 11.98, decrease in Y. Y being the feeling thermometer. Why the decrease? It's a negative. The coefficient is negative, therefore it's a decrease. If it's positive, it'd be an increase, right? It could go either way. So, now, let's look at our R squared. We have 0.45 compared to 0.05. I'm sorry, did I say 45? No, 0.045 compared to 0.05. Since this is greater, this is higher, we would say that this model does a better job at predicting Hillary Clinton support. right? Halo-Clinton feeling thermometer. Also look at the standard error. So for the standard error, for this guy, we want it to be larger, right? For R squared, it ranges from 0 to 1, so the closer to 1 it is, the better the prediction. For standard error, we want these to be smaller, right? We want to explain more things. So take a look at what we get out of here. We can see that they're pretty close, right? 27.5 versus 27. There it is, 6. But still, even using that metric, we can see that male did a worse job. It has more error, more root mean squared error versus the income. Income did a better job. So if I asked you which has the better model fit, it's definitive. They both do it. Now let's look at the last one. There's one problem with the R squared. The R squared, whenever you add variables to a model, even if they only remotely affect the outcome, will increase the R squared. Because look at how the R squared is calculated, right? We're looking at things like the residual sum of squares versus the total sum of squares, the mean sum of squares. So we're looking at how much variation can you explain. And so pretty much by definition, unless you have something that is perfectly unrelated, which is almost impossible to achieve, right? It has to be like 0% correlated with the dependent variable. It's going to always increase, meaning the more variables you add to a model, the more x's, right? You add, the more independent variables that are trying to explain the dependent variable, you will see the R squared go up. So one of the downsides then, of course, is that the R squared, it can be misleading. You're throwing in everything in the kitchen sink and hoping something sticks, and invariably it's going to look like things stick, right? So you keep tossing things in, the R squared is going to get inflated. This is why the adjusted R squared was invented. The adjusted R squared, look at what it does. We have 1 minus, we need the R squared first, right? So we take 1 minus the R squared, we multiply it by the total number of observations. In our example here with our data set, we have 200 minus 1. Divided by the total number of observations, 200, minus p. P is the number of parameters, or, in other words, the number of independent variables in our model. And then finally, minus 1, right? Why are we doing that? Because think about what it's doing. As we increase the number of p's, the number of independent variables in our regression model, we are now penalizing ourselves by then dividing by that increasing number. So here, this denominator in our first model in a bivariate regression with just a dependent and one independent variable would simply be 200 minus 1, because there's only one parameter, and then minus an additional 1. But if we had something like 5 or 6 independent variables, it's going to increase, you're going to see that it's increasingly shrinking that size of the denominator, and then you're going to end up, it's sort of, as I said, it'll penalize you. So what you'll always see here too is that, take a look at our R squared, you'll notice it's smaller in both of these, right? Both of these models than our simple R squared. Our adjusted R squared is always smaller, right? And so what we'll see is that this way it's sort of a better way to look at, which of these is doing a good job given that in the multiple regression setting. Right. In this bivariate setting, it doesn't really matter which we look at. Let's compare the two. So for the income, we had an adjusted R squared of 0.493. Here we had an adjusted R squared of 0.40. So we can still conclude that no matter what method we used, that the income model did a better job of explaining the Hillary-Clinton feeling thermometer than did the model using men versus women. Right. Okay. What else we got? So one of the last things we have to talk about are the confidence intervals around the estimate. So just like we did when we talked about t-tests and some of these other, Chapter 9 we talked about the normal distribution and stuff like that, or 7, that might actually be Chapter 8, I think that might be a typo. We talked about the fact that you can create confidence intervals around the estimates because of course there's going to be an error. And the size of these confidence intervals are going to be a function of the sample size. The larger your sample, the smaller the confidence interval. And so here's, you can see how they're calculated. For the beta coefficient, it's going to be plus or minus. The T statistic, which you'll look to that t-test to figure out what that would be. And remember, once you have basically 100 observations or more, it basically, for 95% confidence interval, it basically becomes 1.96, or as the book rounds up to 2. And then at the 99% confidence interval, it's like 2.5 something. I forget what the exact number is. Yeah, and then you can see that the same thing is for you can see for the beta coefficient and for the intercept, it's all the same. That alpha with the hat is our intercept or our constant. It's the same formula, right? You take the T statistic, the critical T statistic, which is 1.96 for the 95%, and then you simply multiply it by the standard error. Now, there is in your book a whole thing on how you calculate the standard error, but thankfully for our purposes we don't have to do that, right? Because what we can see is that they've already done that for us, right? They've already calculated the standard error. Let me expand this out. So this is our model with men, right? We can see that they've calculated the standard error, right? Here they are. They've calculated the T statistic. Now, the T statistic that they are using is they've also calculated what their the T statistic based on the sample. So they've already calculated that for us, right? The critical T statistic. And then they've also then given us our p-value. So we can, for our purposes, we actually don't, and also too, let's look over here. They've also given us, if you scroll over, they've given us our upper and lower 95% confidence intervals, right? This is pretty handy. Let me see, where's that? There it is, right there. Yeah. Yeah, and so what you'll notice too is that I don't know why they spit both of these out, because I think these are identical. Yeah, they are. These are. I don't know why they have this twice. I'm not quite sure why they do that, but okay. Well, either way, it doesn't matter. So what they've already done here is they said, okay, given this is the coefficient, this is the lower bound, right? And then this is the upper bound. So you might be asking yourself, how did they get these numbers? Where did they get the minus 55% plus 66% from? Take a look at our standard error, and remember for the 95% confidence interval, the T statistic for basically over 100 observations is about 1.96, right? So I could say equals 1.96 if I want to know the 95% confidence interval. Multiply that, use the asterisk, times the standard error. Ta-da! Now take a look. If I do equals the coefficient and I add it, so this will be the upper bound, and then if I do equals the coefficient and then I do minus this, that's the lower bound. Now you'll notice that these numbers look almost identical. They're a little bit off. Why are they a little bit off? Because it probably wasn't 1.96, it was probably some other value. I'm just using 1.96 because it's pretty close, right? It might have been a little bit less, a little bit more, and so that rounding issue is what accounts for it. There's also then an easier way to do this too if you want to know what this is, rather than multiplying it by the critical value, because maybe you don't want to look it up on a t-table. Here's an easy way to do it too. So I want to know what the margin of error plus or minus from any given thing is, right? Well, what you could simply do is you could say, okay, well, why don't I just take the coefficient? So this equals the coefficient of the intercept, right? 60.707. And then why don't I simply subtract the lower bound? And then there it is, right? So so then I can say, okay, so then the confidence interval around it is plus or minus 5.3 basically, right? So this then that would be our 95% confidence interval, plus or minus. Now, of course, if you want to get the 99%, all you'd have to do is, when we went up to here, and I used the 1.96, instead you go to the t-table, you look up the 99% confidence interval for whenever you have 200 observations, and then you would use that critical T statistic. And that's the one, of course, located in the back of your book in like appendix, I want to say like A or something like that. I got it up here. Where is it? Appendix B, right? So you just look at degrees of freedom, which is your number. It has your number of observations on the left column going up and down, and then you have your whatchamacallit, and then whatever confidence level you want to look at. Okay, the last thing I want to show you is, what if I ask you to tell me what if I ask a question like this? Let's go to our model that has the residuals on it. Here we go. The predicted, well, yeah, actually, let's stay with men. Let's stay with men because this one's super easy. So we've done this regression with men, and I ask you this question. What is the expected, now that you've run this model, what is the expected value of support for Hillary Clinton on the feeling thermometer for men and for women? How would you calculate that? For this one, it's super, super simple, because all you have to do is plug in the values, right? Plug in the values that it could assume. For this one is super simple because the male value variable can only assume two values. It can only 0 or 1, right? It's a binary, it's a dummy variable. It can't assume anything else. So I could do something like this. So we know that male is coded as 1, so we'll say 0. We'll do 1, right? Those are the two values. So these are my predicted values given my estimate of my model. I would say equals my intercept plus my constant. That is always there. It's right. It's constant. So this is an additive model, right? Because remember what our model looks like. Let's recap how this thing is going to look. It's y equals a plus coefficient, which is also called the beta symbol, right? The beta coefficient, times the value of x, right? So all I need to do then is take equals the intercept plus the coefficient, this guy, right? Coefficient for beta, multiply it by 0. Now, of course, you can see that when you multiply anything by 0, what's going to happen? It's going to be 0. So what's it going to say? It's the exact same thing as the intercept. Now, Alternatively, what if it's a male? So this is for female, right? Male equals 0. I would say equals intercept plus male times 1. Why? Because it's male. And now I get that result. So that's my predicted value for, this is for female, this is for male. Those are my expected values of y. Now, what if I have something that's a little more complicated, like this, right? So this guy has 24 possible outcomes. It's not that hard. What you could do is that it actually does it for you, right? But the thing is I'd have to look here. This is kind of a pain in the butt because what I'd have to do is I'd have to look at these are all the y hats, the predicted values of y for all the different respondents from this data sheet. So what I could do is I could find a respondent for every single one of these, right? And then match it up and do it that way. But that's a pain. There's a much easier way. Let's go to a blank sheet where we don't have those pasted in there. I've got my income variable. I know that income ranges from 1 to 24, right? So all I got to do is create a list that goes from 1 to 24. So I could either manually type in 1 through 24, but that's a pain in the butt. There's an easier way. I'll type the number 1. I'll say equals 1 equals this cell, which is A20 in this case, plus 1. Now look what I've done. Now it equals 2. I could copy this, paste it all the way down until I get, I only need 24, right? Because I don't have any more than that. Can't go higher than 24 in the income variable. So now look what I've done. I've got a nice number that I can use as a multiplier. So now I can do this. Remember what we're doing from the other sheet. Let's copy this guy and paste him. This is what we need to do for all the values, right? It's actually pretty simple because all we got to do is type it in. So I'm going to say equals. Now, the trick here is you might be tempted to say, okay, equals coefficient or equals intercept coefficient, right? But you want to avoid doing that. You want to manually type it in when you can. And here's why: because when I copy and paste this thing down all these cells here, down this column, it's going to move downward. Let me show you what I mean. If I select this and then I say plus, open parentheses, just to keep the operations easy, this guy times this guy, it's going to give me the correct answer. But look what happens when I copy and paste it. Control C, Control V. Now look what it selected. See, it's selected. It's assuming that every time I go down one column, one row here, that I also want to go down one row here as well, and that's wrong. So the easy solution is this. Instead, I'll say equals intercept. I'll manually type in the value. 70. Don't worry, you only have to do this once. 101 plus open parentheses. Now I can click this guy because these things are. I do want these to move down, right? Multiplied by manually typing the coefficient for income, negative 1,01805. Close parentheses. Hit return. Ooh, I think I did something way wrong here. Oh, I forgot to put a decimal. I was like, that's a giant. There we go. Ta-da! Now, take a look at what I can do. Da-da-da-da-da-da-da, and paste. Did it. So now I can say, okay, what are the predicted values of y for the feeling thermometer for Hillary Clinton for all values that income can assume? All I got to do is put in all the values that income can assume, 1 through 24, and then just plug in the simple formula of this, right? Your intercept plus your coefficient times that value of x. So when we do multiple regression, when we add in more independent variables besides just income, you'll do the same thing, right? You can simply plug in those values and then create those predicted values of y all the way down. So what I could say is, okay, and then I could ask you questions like this. I could say, I don't know what the average is for income. Let's go find out real quick. So let's do equals average. Income is C2 through C201. The average income is 14.965. So what I could do is I could say, let's assume, where are we? There we go. So 14.965. That's the average income. Now, of course, nobody can answer that because remember, income was coded as 1, 2, 3, 4, 5, all the way to 24. Nobody can be 0.9. But let's say, what would be the expected value of y? What would be y hat for Hillary Clinton on the feeling thermometer for a person that's reporting an average level of income on that income variable? What I could do is say, okay, that's easy. Equals intercept plus open parentheses income times the average value, close parentheses, hit return. And there it is. So we would say if the average level of income was reported, we would expect Hillary Clinton's support on the feeling thermometer to be 55 out of 100. right? 55.075 technically, right? So that's how you make these predictive values. Okay, I hope that's helpful. If you come up with any other questions, let me know, and I can always go back and edit the video a little bit. But that should answer all of your questions. What I'm going to do for data, if you want to practice with this, is let's see what I can do to kind of help you out here. Okay, I've got an idea. Here's your task, and I'll write them down, and I want you to do them, and then I'll show you at the end of the video how to actually do it, and you can check to make sure your work is right. Okay, so here's how it happens. So here's what I want you to do. For one, I want you to make a variable, or generate a variable called female, where 1 equals female, 0 equals male. 2, let's bold these. 2, run a regression. Let's change that up. Let's call it run regression, where y equals Clinton, Hillary feeling thermometer, and x equals female. 3, interpret the coefficient for female, excuse me. 4, generate y hat, or also called predicted value of y, when female equals 1 and female equals 0, or in other words, when the respondent is a male or a female. Okay, those are your 4 tasks. Pause now, try and do them, and then hit play, and I'll go through them real quick. Okay, here's how you do it. First, our first task, we need to create a variable called, let me move these out of the way because I need some space. I need a variable called, piece of crap. Let's just move it down. We'll just move it here, that'll work. Okay, I need to create a variable called female. Let me start it. Female. Oops, that's not how you spell female. So, this is easy. Female is simply the inverse of male, isn't it? So I could create an if function to do it. I could say equals if, open parentheses, if male equals 1, if true, I want it to return a value of 0. If not, return a value of 1. If false, return a value of 1. Now look at what I've done. Ta-da! So what I can do is just copy this, paste it all the way down. Perfect. I now have female generated. Now, run a regression where y is a Hillary Clinton feeling thermometer and x is female. Pretty easy. Go to data. Go to data analysis. I can actually still keep, since we've been using the same dependent variable, I can keep the Hillary Clinton feeling thermometer where it is. I need to change this though, don't I? This now needs to go from I2 to, I'm sorry, not I2, I1, because I'm using the labels. I1 through I minus 201, I think it is. Yes. Close parentheses. Oh, I don't need close parentheses. Just leave it there. And that's all I really need. Okay, cool. Cool. Here's our results. Let's copy and paste the rest of those tasks. Why is that over here? Oh, okay. Don't really need that. Oh, here we go. Copy these tasks. Where are you? Where did she go? Is this it? Yeah, this is it. Okay. So let's paste these tasks up here. So task number 3, interpret the coefficient for female. The way you'd interpret this is that being female, or a 1 unit increase in female, in this case, since it can only assume 2 values, it'd be kind of weird to say a 1 unit increase in female because it's either there or it's not. But we could read it that way. So a 1 unit increase in female increases, support for Hillary Clinton by 11.98 points. Or, to word it another way, being female increases support for Hillary Clinton by 11.98 points, all else being constant, or you could say all else held equal. The reason why I say that is because I'm assuming when you get other variables in the model, I'm not changing those, I'm just changing this one, right? Cool. Now, generate a y hat, not y hat, for the predictive value of y, it's possible assumed values. Remember how we do this. So the predictive value for y hat equals alpha, which is our intercept, alpha hat, plus beta coefficient, which is here 11.98, times whatever value of x we want it to assume. Here, it can only assume 2 values, 0 or 1, right? So, I would say this equals intercept plus this guy times this guy, which is the value of x. Repeat this. Now, of course, it's the same thing as just the intercept because you multiply it by 0. To get the other one, you do this equals this guy plus this guy times 1. We get 60.707, right? So this would be if female, that's their expected value for y hat. This would be for males, right? And that's how you interpret it. And then also, you'll notice too, by the way, if those numbers sounded kind of familiar, look back when we did the male version. Where is it? Notice it's the exact same coefficient, except it's positive this time, right? That makes sense, doesn't it? Because we've done the exact same variable, we've just recoded it slightly, right? Well, not slightly, we just inversed it, right? Okay, so that's how you do that. All right, that's it. Hope to help.